continue along the path that started with yesterday, and to also move on after discussing the chemistry part to really get now into the more interesting part is understanding, or trying to understand, the ordered phases that occur in the nuclei. And I'm going to put focus on magnetic transitions, how they may be related or connected to structural phase transitions and superconductivity. As before, I put the references up at the front, so at least you have them. And also, let me say what I said again, or said yesterday, that there are many people here in the audience who are citing, in fact, a lot of their papers. So please make sure that students get an opportunity to talk to them and to hear their perspective on the nuclei. I mean, as we saw in the morning, it's quite a rich field, and the story is by no means done. There's a lot left to be written on these materials. Okay, so first I want to discuss viewpoints on magnetism, a way of thinking about magnetism in iron nuclides. I mean, we've seen that they possess, in almost all cases, an antiferromagnetic state at some region of the phase diagram that gives way to a superconducting part. And the order that appears is not like in the cuprits in terms of a checkerboard pattern formed of localized spins being an insulator, but is metallic spin density wave state, which forms this collinear pattern of spins aligned along a particular direction and anti-parallel with another side. So that's looking in the one iron unit cell, which is always the way that I like to think about things, is a pi zero type of ordering. And that's another difference with the cuprits is that there's a structural transition, as we pointed out already, that in some cases lies very close, if not on top, of the antiferromagnetic ordering temperature in the parent compound, and then it splits with doping or stays split with doping as you move away from the parent compound. And then the orthorhombicity kind of end magnetism gives way to the superconductivity, and it's very tempting. Oh, I'm already using this again. To make a connection with the quantum critical point of where antiferromagnetism lies, that superconductor, or the critical point here where antiferromagnetism goes away, is somehow connectable to the phenomena of TC or maximum TC itself. So what I'm going to try to discuss are two different viewpoints of looking at this. One from the point of view of itinerant electrons forming a spin density wave due to nesting, such as in chromium. So that's a decoupling type of approach. And the other is to look at, thank you. That's and the other is to look at things from the point of view of how things work in the cuprits, of going to a more local moment picture and looking at Heisenberg or extended Heisenberg models. And I think this paper by Michel Johannes and Igor Mazin really kind of pointed out that both ways of looking at things have their advantages and also disadvantages, and probably neither is completely right in and of themselves. So that's kind of the goal of what I want to discuss here. So here are three different things to keep in mind when looking at magnetism of these materials. So one is that everything is being governed by details of the Fermi surface nesting, how well the whole pocket can be put on top of the electron pocket, and having a nesting condition be satisfied with the pi zero wave vector that orders them in the one iron unit cell, or the diagonal wave vector in the two iron unit cell. So there, what you'd expect is really magnetism is going to be governed by subtleties of the Fermi surface itself, and orbital content could be playing a role there, because as you see, the orbital content, of course, changes going around the electron pockets and also going around the hole pockets. So on the opposite side, there's not really, there's a smaller role of Coulomb interactions in this one, but the other approach is to start with the spins being localized and expand in what you hope is a small parameter, which is some type of hybridization with iron to its neighboring iron or iron to arsenic over something like the charge transfer or any of the Hubbard U's, and try to build up a model in the language of spin-only Hamiltonian. And this is fine as long as it's always fine to be able to do this. It's just a question of how far out you have to keep going in your parameter T over U, T over delta. And of course, if things are itinerant and you're being dominated by large kinetic energy, that means you'd expect to have an effective long-range spin interaction. And then the third thing to keep in mind is the role of the intra-atomic Huns coupling. That is kind of neither of these. It's really connected not with something happening within the window of the Fermi surface, but connected to all the orbitals that are extended, that are occupied, that gives rise to all of these magnetic states that we saw in the Tsunami-Sugano diagram in terms of those particular levels from just a single atomic point of view. So that's the reminder of the role of Huns in giving a high-spin system. So let me first look at the role of local density approaches and thinking about magnetism. And there's been quite a lot of work here, and I again confess of not being able to really capture everything that's been done. I'm only picking selective references to discuss. So early on, LDA was sort of combed in order to determine what was the magnetic ground state that would appear, putting in a particular type of order and looking at what its energy gave and trying to find out what the lowest state was. So that included looking at ferromagnetic states, checkerboard, antiferromagnetism, as over here, or the striped antiferromagnetic order, which is over here. And it turned out that for most studies, almost all studies, the striped antiferromagnet wins for all doping. And that can be qualitatively described in terms of an Heisenberg-like picture where the long-range next nearest neighbor interaction of going from iron to arsenic onto the other iron could be quantitatively as large or maybe larger than just the nearest neighbor iron-iron exchange. And so that would tend to favor an antiferromagnetic, collinear antiferromagnetic state if that hopping J2 is bigger than half J1. And so this is, again, connected to the large itinerancy of the iron states, and of course it will be sensitive to the details about structure if we're really concerned with band structure effects as LDA is. So LDA does a good job of capturing Hund's physics, and I think as a reason of that, it tends to overestimate the large magnetic moments that come out from LDA. So here's a table of the different ways of implementing LDA from using different approaches. So here's the magnetic moment that's here in terms of using either optimized coordinates or experimental coordinates of the structure. And so you wind up seeing that things are on the order somewhere between around 2 in terms of EUV or magnetons per ion. So this is smaller than the full saturation of 4 Bohr magnetons per iron, which would be, if you just had Huns and no hybridization at all, that's what you would have. But the experiments are substantially below this, at least in a couple compounds. The 1111 compound is about a half Bohr moment, the 122 about 1 Bohr moment, but higher in the tellurides, and even higher still with the new compound, the potassium XY2 or 112 that was discussed earlier this morning. And so I'd say that LDA is quite good at understanding magnetism, but then the real issue is how can we get these magnetic moments to agree more with the ones which are observed experimentally. And so the two issues about the weaknesses of LDA are certainly it's in essence a mean field theory, so it's not going to capture spin fluctuation effects, which would tend to destabilize the overall magnitude of the moment. And it also, if strong Coulomb Hubbard type physics is involved, that certainly also wouldn't be captured. That's a well-known problem in LDA predicting metallic behavior in materials which are not insulators. And so one of the things that has been discussed is how can we think about that essentially right. Now we need to understand how can we bring these moments down. And I think one of the areas has been raised in terms of domains which can possibly be formed, in which things are antiferromagnetic with large moments inside a particular domain, but for some microscopic reason connected with something we don't yet quite understand. The system likes to go into nanoregions, or not nanoregions, sorry, that's a Kubrick terminology, but longer regions which on average point in different directions and give an average much smaller effective moment. So this is a way in which you could reconcile LDA and in homogeneity of giving smaller moments, but it raises a number of questions of what sets the length scale of these domains, what are the dynamics of the domain walls themselves and how do they fluctuate, is there a time scale connected to it, and can experiments, have experiments been able to detect this, that there is a length scale and a time scale, and if not, then are these domains fluctuating faster than the experiments which would be sensitive to this local order to potentially measure? So that's one way of trying to thinking about reconciling. Another is to look at the connection between the structural transition. Go back. So this line here is very different than in the Kuprits. This thing just seems to hug the antiferromagnetic phase boundary. So LDA has also weighed in on that in terms of understanding things from the point of view of structural changes. So here, this is a slide that I stole from Peter, but one could understand that the structural transition of making things orthorhombic in 1, 2, and 1, 1, 1 might prefer to have a particular orientation in which way the magnetism might go, lending to the physics of the crystal field exchange and the role of Huns, plus delocalization, so that that is connected to this particular type of order. And in the 1-1 compounds, the structural deformation could lead to the formation of double straight materials. And this has pretty much come out from LDA, that it correctly predicts the connection between the structural transition and the magnetic transition, but it requires magnetism as a prior condition for distortion. So you saw that the phase transition lines are separated, and of course there's a question of the order of each of the transitions. But I think basically it does well at capturing this because of the two areas that we discussed yesterday, this competition between changing crystal field effects due to Huns physics due to changing the structural parameters of the materials. So let me discuss the other point of view, which is a more strong coupling point of view, and how that can be connected to a lower value of the magnetic moment, and also connected to how that could be related to the structural phase transition. So as I said, in one particular way of looking at it is to take an extended Heisenberg model. Here's two that I've written down, which has a nearest neighbor exchange between effective spin sitting on the iron and the next nearest neighbor exchange, J2, and a way in which the moment can be controlled is by looking at a quantum critical point, so-called order by disorder effect, where if J2 is on the order of a half J1, that separates two competing phases, a checkerboard antiferromagnetic order from a collinear antiferromagnetic order, with critical points sitting in between them when the fluctuations become very, very strong. Yeah?
Does that only apply in 3 dimensions? Is that a 2-dimensional model? Or is it high dimensional?
Well, there's issues related to dimensionality about Holmberg, Merlin-Wagner theorem, so strictly speaking, we have to worry about always a coupling in the third axis. So I'm going to come to this. It's a little bit further on in the slide. Yes?
So can you comment on what is the justification to just mapping it to a J1, J2, these multi-orbital things? I mean,
well, I think as we've heard in a couple of the lectures.
I mean, I'm not saying that you should take further interactions, but also that, you know, it might not be a single spin on each side or something, that it's more like also taking into account the orbital centers. like a more complicated strong coupling version of a multi-orbital?
Yeah, I'm going to try to illuminate that. That's actually this part over here, which is how the orbital degrees of freedom play a role as well. So this is a spin only. Just give you
But it still would be a single spin at each side, something like this.
no, it doesn't have to be. It doesn't have to be at all. Okay.
Okay.
Give me 2 slides, and then you could ask the same question again. Okay. So this J1, J2 model has been studied by a lot of people, looking at ways in which that could then map onto the magnetism. And then another way is to look at, so this is a frustrated model because the system doesn't know if it wants to be this or be that. So here's another particular model. Again, it's a Heisenberg-like model, but without any frustrations because the magnitude of the exchanges, J1A and J1B, are taken to even be of opposite signs. So J1A, which is connecting nearest neighbors, could be antiferromagnetic, but J1B could be ferromagnetic, and if that happens, then the system, of course, will like to align in this collinear type of fashion. So the way in which that could happen is, I was hoping there would have been a discussion about good enough counting-weighted rules during the talk, but during the talks, but that hasn't occurred. And the way to think about that is if you have an orbital type of ordering where you have only certain types of orbitals which are occupied, then if you have the same type of spin, you could be polyblocked from moving to one of the other orbitals, or you could be promote antiferromagnetic exchange going along the other orbital direction. Is if these orbitals weren't uniformly occupied, then it would just be the usual type of exchange mechanism going across from one orbital to the next. So the connection of orbital order, which is going to break C4 symmetry, globally could be connected to the fact that J1A and J1B could be very different, in fact, even switch sign. Yeah?
But just to be sure, in order to have J1A and J1B that different, you would have to have an occupation difference of the 2 orbitals of order 1.
Yeah, in order to swing it at that size, you need a big net effect on the orbital moment.
There is structural phase transition in this system. Is it possible that it's connected with this orbital order?
Yeah, next slide. Yes.
So are you saying that the orbital degrees of freedom in this anisotropic model are kind of integrated out and that they're incorporated into the signs of J1A and J1B?
Yes. In fact, I'm not supposed to talk about my own work yet, but we looked at a particular model in which you have, actually it's a generalization of the other models that have been discussed, in which you have an orbital occupation which sits here. So that you have one type of exchange if the orbitals are occupied and another type of exchange if the orbitals are not. So I buried that in this J1A and J1B. That's the idea, that these are orbitally dependent. Okay. So if we just take the point of view of trying to distinguish between having a frustrated model, like J1, J2 model is understanding a connection of the low moment and structural transition, and just an anisotropic unfrustrated model, one could look at the inelastic neutron scattering and try to draw some conclusions there. And so what it can do is just fit the dispersion that comes out from neutron scattering, and one can see, particularly along this 1-1-1 direction, that in the frustrated model of J1, J2, which is trying to decide if it wants to be a square lattice, a pi-pi wave vector, or a pi-0 wave vector, the depth of this minimum will be controlled by how close you are away from the critical point. And so this should produce, if you're near a critical point, should produce a local dip around that ordering wave vector. And the J1A, J1B, J2 model is unfrustrated, and that has a maximum sitting around pi-0. So at least in terms of these two models, the neutrons seem to favor a J1A, J1B, but with very anisotropic couplings. In fact, one of them being ferromagnetic, the other anti-ferromagnetic, with a ratio of a factor of 10. But of course, that's just an issue of just truncating this at J1, J2. One could do better by including next nearest neighbor or further interactions. So J1A, J1B, J2A, J2B, based on orbital order, and here's a prediction of what the spectra should look like. or J1, J2, J3, so this is another model with strong frustrations, again producing dispersions which are quite similar in both these cases. So it's not just looking at the neutron spectrum by itself and its dispersion, but one should look at the intensities and understand the dispersion over the entire zone, the spectral weight and the dispersion over the entire zone. So I think this gives a good way to think about things, but of course this doesn't capture the fact that we have good Fermi surfaces. And I saw somebody had asked the question on a wiki, is it possible to have some of the electrons running around giving you a Fermi surface and another species of electrons which are giving you the magnetism? And that's a very good question. It's a way to have both of these itinerant plus localized spin approaches fitting, but I would say that that's just another extreme way of thinking about things at the moment.
What about volume of any sort of largeness theory? Does it include all electrons, including those which you prefer to treat localized?
You mean experimentally controlled?
Experimentally, large volume.
I could comment about that, but maybe Adam is probably more of the expert here. Maybe we should comment on that.
It's somewhat difficult to say because we don't have a full mapping of a 3D dispersion on several cuts. And doing quantitative comparisons is quite difficult at this stage.
What about
Yeah.
Veronique?
I know maybe
Veronique,
Veronique
yeah?
also.
Yeah, I agree with that.
Very well. Do you want to say something?
No,
Okay. Yeah, the Ledinger count is a delicate matter because of the surfaces also.
The Husman alpha experiments, although they're done in the ordered state, have very small pieces. They don't show
Maybe
large.
it doesn't show all the pieces.
Yeah, of course.
They often happen.
Yeah. Okay, so
How long are you going to be?
someone have another question? No? Okay. So here's some recent measurements, neutron scattering measurements from Devereaux et al. Just a little while ago posted. So here is the dispersion of neutron scattering, showing that you have spectral weight, which is extending out to about 200 or so millielectron volts. So that means that the single magnon bandwidth may be up to 200 millielectron volts. That gives a J, in a single Heisenberg-like model, which is on the order of what it is in the Kupitz. And if you try to fit the spectrum to a Heisenberg-like model at low energies or at high energies, you find that you can give a very good fit for the dispersions that I showed on the previous slides. But the AB anisotropy means that it has to be very different along one direction compared to the other. And you could also provide a fit using an itinerant model alone. In particular, what that's good at capturing is the smearing out of the excitations which extend past 100 millielectron volts or so. That's called the Stoner continuum, that eventually your magnon dispersion enters into a big particle continuum which will damp the spin rate. And so that's been pointed out in a couple other references. So if you look at, so that you wouldn't be able to capture in a spin-only model, you'd have very well-defined excitations all over the zone. So you see that two different ways of looking at things are not completely mutually exclusive. But here's an issue that is, I think, really can be connected to what's the relevant physics, which may connect the structural transition with the magnetic transition. So this is data from Ian Fisher's group in 1-2 compounds. So here is the phase diagram of the structural transition followed by the magnetic transition, and superconductivity is there. And by using a particular clamp to get rid of twins and looking at a single domain of magnetism, they plot the resistivity along one direction and the other, along the A direction and the B direction as a function of doping and as a function of temperature. And what they see is, as you cross this line down at near the antiferromagnetic compound, that there's a bit of anisotropy along A and along B, so you may think that this may be related just to the difference in the length of the A and B direction. But then the anisotropy, as you keep moving out and doping, gets very, very big. gets on the order of a factor of 2 or so as you go through the structural transition, and then followed by the magnetic transition. And the point is that the anisotropy starts to develop above the structural line. Now, this may be related to the fact that there's a clamp, so that's providing a symmetry breaking, but it's still happening at substantially higher temperatures than that line. And so this is a color plot which is plotting the resistivity anisotropy going up to a factor of 2 as you're getting closer and closer to the point where superconductivity is coming up and the magnetism is going away. So if you look at the magnitude of the structural distortion, you see that this is less than 1% or so, and it comes down with doping, whereas the transport anisotropy is a factor of 2 and goes up as one increases doping. So there's been a lot of work connected to this in terms of looking at that this phase, that is lying above the true magnetic transition, is related, doesn't have truly long-range order, but it's got some other type of order, namely electron pneumatic order, that may be connected, for instance, to orbital ordering, or it could just be connected to being a spin pneumatic. So let me explain what that means very quickly. So these are the type of questions we like to ask. I should also mention that this type of anisotropy has also been seen in photoemission, superconductivity, and magnetotransport, so it's not limited just to the transport measurements. And so in the context of a spin pneumatic, I have a number of slides in here, but I'm going to kind of go through them quickly. They should be posted, so hopefully you can look back and ask questions or follow up with me a bit later. So this idea is taken over from liquid crystals, in which there's orientational order, so that the order parameter is not a vector, say, pointing in a particular spin direction, but is an axis where, say, the sublattices of the spin on each neighboring site are always pointing in parallel or anti-parallel, but they're allowed to rotate together with each other and give no net moment, but yet have a well-defined order parameter. So that there's an axis which is selected, but not a particular direction of a vector. And this has a very long history. It comes back to the early days of high-temperature superconductivity in terms of formation of quantum spin liquids, as we heard a little bit earlier today and later on. Some more will hear about that, and how to get magnetism without any moments. And so this is a state which the average spin operator has no expectation value, but S dot S is non-zero. And so classically, you should be able to rotate these two vectors along at no energy cost, and the quantum fluctuations help to select a particular order when it does form. So, and in fact, recently theoretical models have given emphasis to this in terms of adding a biquadratic term to the Hamiltonian, the Heisenberg Hamiltonian. But the question is whether or not that's realizable in real material.
Can you mention something you have these silver nickel what is it about, right?
Well, I think that's, again, trying to look at this material and understand is it a frustrated magnet or not.
What's so specific? Kind of distortion, but
Can I talk to you about that a little bit afterwards? I don't want to get too far out. Yeah, again, connected to structural matters. So this has been discussed in the context of the relevancy of the nuktides, of understanding why the magnetic and structural transition are in fact related to each other and are split by many different groups, and they're listed in the references. I would say, due to time, I'll kind of pass over this, and we can discuss it a little bit later. But dimensionality, of course, plays a very important role with this and that magneticity. So let me then finalize by discussing the way in which the spin fluctuations have been incorporated, and there are many different ways in which that has been done in the context of a weak coupling, a random phase approximation method, or a recoupling functional normalization method of looking at stabilities of various ground states. And a lot of work has been done in dynamical mean field theory, and this is a snapshot of lots of results from DMFT from Devereaux' group, which by including the dynamic fluctuations in at least the DMFT-like model, one can get values of the moments which are much lower than what you would get from LDA alone, and correspondingly one gets values of the effective mass in terms of interaction parameters, or the strength of the interaction, which is not huge, but it's on the order of 2 to 3 in terms of band masses, and it has some orbital content, orbital dependence. So I think sorry, I forgot, I should mention, of course, I think this will be discussed about how this could be done in the ordered phase magnetic state in this talk, which is following mine. So I think that in looking at the progress that we've done in understanding magnetism, putting together LPA plus some type of fluctuation certainly does a pretty good job of understanding the ordered phases themselves, how they may be related to structural transitions and values of the moment. But the importance of the orbital part, I think, is still very much an open question. How strong of a role is that a driver, is that a bystander in the magnetic order? So, and again, I think the importance in all of this is the role of Hans coupling. So in DMFT, so you could ask the question after going through the exercises, are these materials strongly correlated or not? So here you see band masses, which are only a factor of 2 or 3. So that's, you might not expect correlations to be doing all that much, but DMFT, at least at the beginning, was producing lots of different results. 5 minutes, oh my God. Okay, good. That means lecture 3 is going to be completely different. Please delete what's sitting on the web. All right. Anyway, the point is that there were very different statements. That in one particular study from Gavi, the system was considered to be a bad metal at the verge of a metal insulator transition, with the values of U, which are just about on the order of the bandwidth, maybe a little bit smaller. But another DMFT calculation actually concludes the opposite, that it's a weakly correlated electron structure with maybe a renormalization of a factor of 2. So now in terms of superconducting pairing, this is probably what a lot of people want to see more, so I think I'm not going to make it all the way through in 5 minutes, and I don't want to rush, so I'll just put it off to, I'll keep going till I use the 5 minutes, and then we'll stop. So the idea is trying to understand the formation of superconductivity from our standard model, which is identifying what is the mechanism, what is the glue that brings the electrons together. So this is the usual case in terms of electron-photon interaction, that the lattice responds to the electrons as they move by, creating a little pillow, that the next electron, when it comes by, falls into the depression of the lattice. That's our standard model for electrons to pair, but we don't necessarily need there to be a lattice that could be involved. It could be just like in the case of helium, where a neighboring atom can polarize another atom and form an attraction which is purely electronic rather than connected to a lattice. So in terms of the role of the lattice in the pnictides, I think early on it was established that their electron-photon coupling can be connected to the mixed vibrations in iron and arsenic, which are sitting around the 200, 300 wave number energy range. But the lambda that comes out is 0.21, so that's not very strong. And if you take a sort of a Debye frequency to form your superconductivity, you find that that's just not strong enough, not enough juice to provide strength to form a superconducting state. And the reason for that is actually pretty straightforward, is if you want to gain energy from the electron-photon interaction, you have to modulate a lot of the bonds that are connecting, say, iron to iron or iron to arsenic. And if you look at that particular the iron to iron orbital, that would be most sensitive. It's this x squared minus y squared one, which would be sensitive to this modulation. And because of the EGs being inverted, this guy is sitting below the Fermi level. So you'd expect anything which is connected to superconductivity local to the Fermi, or connected to the Fermi surface, you'd have a weaker coupling there. So this may be important for magnetism, which is extending over a larger energy region than superconductivity, but anyway, the point is not strong enough. So that, I think, has led a lot of people to come to the conclusion that repulsive interactions are at least playing a dominant role. And so maybe I'll just do this little introduction before time runs out about how to think of the way in which you can get superconductivity from purely repulsive interaction. And it's quite simple if one looks at the BCS gas equation. If V is attractive, meaning V can be negative here, this minus sign cancels this minus sign, and we can get a solution to the gap equation where delta is just a number or mildly K dependent. But if V is repulsive, meaning that connecting the state to K and K prime is always positive, then the only way you can satisfy the gap equation is by having a gap change sign. So if the repulsion is big and peaked at large wave vector, like at pi pi, in the case of a checkerboard anti-ferromagnet, then for the two states K and K prime connected by that wave vector pi, you just switch the sign. And so that's, this is from Jenny Hoffman, that's what how it relates to the cuprics, where the order parameter can pair electrons at fermion state K to another one K prime, which are connected by the antiferromagnetic reciprocal lattice wave vector, and the gap changes sign plus minus, and gives D wave pairing. And the same can happen in the nuclides, where you can take this Fermi surface and move it over to that Fermi surface with a wave vector of pi0, and so then you could imagine changing sign by having a gap of one sign here and a gap of another sign here. You don't need to introduce nodes in order to be able to do that.
Is Nathan good or bad for this mechanism?
Good and bad. I think largely in the context of recoupling, it's fairly good, but in connection with beating magnetism, not so good. Sorry, it's not a simple answer to the question. So, so this is what Igor pointed out in 2008 for the nuclides, that type of repulsive interaction would just give you, since these Fermi surfaces are not too big, you could expect to have one sign of a gap on the hole pockets, another sign on the electron pockets, and that would be just the S plus minus type pairing, which has been followed up by many different people, and so this band-band scattering can give you this S plus minus state. So this is a good idea, but it really stems back to the work of Harry Sewell, who looked back in 1959 at the idea of having superconductivity multiband system. And here's his equation for TC in terms of intra-band scattering, say VDD or VSS for the two bands, and interband scattering, VSD. And so if you switch off that interband scattering, the only solution you get for an S-wave superconductor is to have these V's be negative. But if you turn off VSS and VDD, this is a simple exercise to see, you also get a solution to this equation up here. And so you can get a pairing where the solutions are allowed predominantly because of the interband scattering being repulsive. And actually, this is a bit amusing that this actually came up in the context of ITC, and I think this is why Igor was very quick to publish this paper that he did. In fact, he and I were postdocs together in Stuttgart when this thing was published, and it turned out to be Igor's first posting on ConMat, which is the idea that he had that the same thing could be going on in the cuprits, where you have two layers of copper and oxygen forming a bilayer, and you could have S-wave pairing on this layer and on this layer, but of opposite sign. That would provide also a solution for the gap equation, and that's being highlighted in this sentence here. So in that context, well, we know that it turned out to be a dx squared minus y squared superconductor. So good idea to revive it for the iron nuclides where this may actually be something. So here is my last slide. Okay. Just the point that I want to draw out is that from a purely repulsive interaction point of view, one can generate either D wave pairing or S plus minus pairing purely from repulsive interactions. Here's the D wave pair state. This is the Nick-Titus plus minus state, which is moving, giving a different sign of that orbital and that orbital. And if this orbital goes away, so that's the one sitting at the gamma pocket, then the only way that you can get pairing from a repulsive model is to have the gap change sign going around on the electron Fermi surfaces. So that would be a dx squared minus y squared pair state. So because I've run out of time, I think I'll stop there and then I'll dive into more models connected to superconductivity in the last section. Thank you.
Yes, so you talked today about these two transitions, the orthorhombic and the magnetic transition. And the phase diagrams that I think you showed and some previous speakers showed, it seems like these two transitions sometimes happen at the same point, sometimes they appear at different temperatures, and there are compounds where they are in undoped situation, they are at the same point, and as a function of doping, they are. So people tend to invoke this model of Premian Chandra and the explanation, but what worries me there is that the coupling, so basically the relevant parameter for having two or one transition there is the dimensionality, the coupling in the third dimension. And what you have is either two second order phase transitions or a single first order phase transition on a line. Right? So it will take a tremendous coincidence to be right at the critical endpoint of this single first order phase transition, and then so with doping you will split the transition. So is there any alternative explanation for
In that particular language
Yeah.
of J1, J2,
Right.
not that I'm aware of, but please somebody who's if they have an opinion about that, chime in. That's precisely the issue. So you can look at that in the context of Ginsburg-Landau, and then you could determine what a magnitude of the coupling could be in order to produce that terminus point. Maybe Daniel's going to.
Yeah, but Ginsburg-Landau doesn't give you the right phase. The right phase diagram.
I agree, but I don't want to say anything that.
No, actually, I have two questions. One is when discussing kinetography, we contrasted kinematic or orbital. But aren't these things in principle conceptually rather similar? Because kinematics is actually average of a square. A square is the same as electric quadrupole moment. Electric quadrupole moment is expressed also by a square.
Right.
So kinematics is the same as electric quadrupole, and orbital orbit is also electric quadrupole.
Right.
Maybe kind of details are different, but conceptually these are similar. Right?
No, they're not completely orthogonal to each other, and maybe.
Both cases are electric quadrupole orbit, effectively.
Right, and you get an orbital moment even in this particular kinematic state, which can.
Maybe in case of orbital degeneracy, simply numerically stronger and mathematically somewhat different, but conceptually it's very similar.
Conceptually, it's very similar. It's a question of magnitude. How big is the orbital moment that comes up? I don't know if you're going to discuss.
And second question, actually, when you discussed all this in the document, you always had in mind this 111 or 122, but what about 111, which magnetic structure is very different? Can you compare it somehow?
I don't know of any
I don't
transport
know.
anisotropy that have been done in that. I'm certainly not aware of any orbital moment coming from photon emission.
Magnetic structure is very different.
And yes.
I'm aware.
Yeah.
Is there also structural tradition? I simply don't know.
In the 1-1.
I don't know. This different magnetic structure, but these are also similar structural tradition or not?
Drawing the
There's
plan.
a trigonal.
Huh?
There's a trigonal.
Remain right, yeah. Not right.
Yeah.
Also in superconducting, selenite number.
So all the superconductors are tetragonal except for these small coexistence regions.
1-1. Yeah? No, I mean
1-1 is tetragonal.
So it means that actually this structural tradition maybe it's not prerequisite for superconductivity. No, so you just
That's the question.
Do you see any connection between this nematicity and the superconductivity, or is it just the peculiarity of this magnetic?
That's on the next couple slides, but yes, in fact, when you start thinking about superconductivity and the role of orbital degrees of freedom, then you could start thinking about should you try to pair like orbitals or orbitals which are different. And that's that's really when the nematicity, right, if you have an imbalance of one orbital compared to the other, will impact the superconductivity. So, you know, a difference in application of one orbital compared to the other.
So you showed the Fisher results for the transport anisotropy, and particularly in the temperature range above the structural transition, the reasoning of Fisher and collaborators was basically that there was a strong pneumatic susceptibility in the system, where if they applied a tiny stress with their anvil, whatever it was, they would see a screw. Yes, they would see an anisotropy, which makes a lot of sense in many ways. But there are other claims, other experimental claims, at least that have been presented, which suggest that it's actually an pneumatic order which exists above that structural transition and not just the pneumatic susceptibility. Is there any progress on understanding that dichotomy?
Yeah, so what Peter is pointing out is the measurements which have been done by the Japanese group in when one takes very, very small samples, and so you have
Just talk louder.
If you have very small samples, so you know they're all within one particular domain, and then you don't have any at least applied stress. There may be some strain effects to the size of the crystal itself, and then torque magnetometry measurements have been done and has seen this anisotropy at huge temperatures, right? Much above the structural transition. That's the last word I've heard on that. I've not heard anything.
And the photo emission?
Nothing.
Maybe I think this is very dependent on the system, because I think in potassium dope samples there is no anisotropy of resistivity above TSO.
In a clamp?
It's very peculiar cobalt dope samples in barrier.
Have people been able to detwin potassium? I see.
Yes.
Okay. Uh-huh.
So there's no anisotropy of resistivity.
That's transport measurement.
Transport measurement.
Do you know about the 111s in that case? Lithium iron arsenide, lithium iron phosphate?
No. So maybe you have to get off the discussion. Because